Now, the second derivative can also be used to test if a critical point, a place where the first derivative is 0 or undefined. So the second derivative can be used to test if a critical point is a maximum or a minimum. So let's say you find a critical point, so a place where f prime is 0. If at that critical point the function is concave up, or the second derivative is positive, then that critical point has to be a minimum. I can see that if I just draw a picture. If at that critical point, that place where the horizontal tangent line exists, if at that critical point the function is concave down, or the second derivative is negative, then the critical point has to be a maximum. If your second derivative is 0 at that critical point, that actually doesn't give you any information, and you have to go back to the previous section where we learned about the first derivative test. So let's see how this works with some examples. Use the second derivative test to find all local extremes. So first of all, local extremes can only occur at critical points, places where the first derivative is 0, or places where the first derivative doesn't exist. So I start by finding the first derivative, which is 3x squared minus 6x. I'm going to set that derivative equal to 0. I can factor out a 3x. I'm left with an x minus 2. So I have critical points at 0 and 2. In the past, we made a number line and analyzed where the function was increasing or decreasing. The second derivative test says we are instead going to find the second derivative, which would be 6x minus 6. And then we're going to take each of our critical points and plug them into that second derivative. So if I plug in x equals 0, I end up getting negative 6. A negative number tells me the function is concave down there, and so that x equals 0 has to be a maximum. If I plug in x equals 2 into that second derivative, I get positive 6. The fact that it's a positive number tells me the function is concave up at that point, and so x equals 2 has to then be a minimum. So I have a maximum located at the point x equals 0, y equals 5, and I have a minimum located at the point x equals 2, y equals 1. Now you can find other higher derivatives as well. You can find third derivatives and fourth derivatives by just continuing to take the derivative of a function. The third derivative we're going to denote with 3 primes, and then once you get to a fourth or a fifth derivative, instead of writing 4 little primes, that's really hard to see, we just put that number 4 there. So for the function, let's find the following. If we want to find the third derivative, we are going to have to take the derivative, and then the derivative of the derivative, and then the derivative of that second derivative. We're going to have to take the derivative 3 times. Now, this is a product, and I'd rather not use the product rule here. I think it's going to get a little ugly. And so I'm actually going to multiply all of this out to make the work a little bit easier. X plus 1 squared is x squared plus 2x plus 1. And if I distribute the x, I get x cubed plus 2x squared plus 1x. So my first derivative would be 3x squared plus 4x plus 1. My second derivative is 6x plus 4. So then my third derivative is just 6. Now in part B, they want us to take x equals 2 and plug that into the third derivative. There aren't really any x's to plug it into. The third derivative is just a constant. You get the constant 6. If there were x's in that derivative, we would plug 2 in for x. And then the fourth derivative, so now I'm taking the derivative of my third derivative, and the derivative of 6, well, that's a constant, so the derivative of a constant is 0. Finally, the last thing we're going to do in this lesson is talk about putting together all the information we've learned in the past couple sections to create a nice graph of the following function. So we're going to do 5 things. We're going to find the domain, we're going to find intercepts, we're going to find maximums, minimums, inflection points, and then put all of that together into a really nice graph. So let's start with the domain. This is a polynomial, so its domain is all real numbers. To find the y-intercept, I'm going to plug in 0 for x, and f of 0 is 80. To find an x-intercept, I plug in 0 for y. X to the fourth minus 24 x squared plus 80 equals 0. I'm going to see if I can factor this thing. It starts with an x to the fourth, so I could put an x squared and an x squared in. And then product of 80, sum of negative 24, minus 20 and minus 4 would work. So x squared equals 20, or x squared equals 4. That means x is plus or minus root 20, and x is plus or minus root 4, which is 2. Okay, part C is asking us to analyze the first derivative to figure out increasing, decreasing maxes and mins. And so the first derivative would be 4x to the third minus 48x. I'm going to set this thing equal to 0, and then I'm going to factor out a 4x, and I'm left with x squared minus 12. So that means x could equal 0, or x squared equals 12, x equals plus or minus root 12. I'm going to put this into a calculator so that I have a better idea of what value I'm working with. And root 12 is about 3.5. So I'm going to make a number line. Oh, can't forget the plus or minus. My critical points are negative 3.5, 0, and positive 3.5. I pick test values in each of these intervals. And then I'm going to take these test values and plug them into my first derivative. Either of these forms would be fine. If I plug in negative 4, I end up getting a negative first derivative. If I plug in negative 1, I get a positive first derivative. If I plug in 1, it's negative. If I plug in 4, it is positive again. So this tells me that the function is decreasing, increasing, decreasing, and increasing. This also tells me that I have a min, a max, and then a min. So I have, let's see, local mins when x is negative 3.5 and when x is positive 3.5. And I have a local max when x is 0. I'm going to get those y values by plugging things into the original function. And I get y coordinates of negative 64 for those local mins, a y coordinate of 80 for that local max. Finally, let's analyze the second derivative. So the derivative of my first derivative is 12x squared minus 48. I'm going to factor out the 12. That gives me x squared minus 4. Set it equal to 0. So x squared equals 4. X equals plus or minus 2. Those are possible inflection points. I'm going to make a table to analyze the concavity. So I'll pick test values in each of these intervals. And then I'm going to take these test values and plug them into my second derivative and see if I get something that's positive or negative. If I plug in x equal negative 3, I end up getting a positive number. If I plug in x equals 0, I get a negative number. And if I plug in x equal 3, I get a positive number again. That tells me the function is concave up, then concave down, then concave up. And these numbers, 2 and negative 2, are my inflection points. So I have inflection points when x is negative 2, when x is positive 2. The y-coordinates of those inflection points, if I plug those into the original function, are 0. So finally, we are going to put all this information together in a really nice graph of this function. So I'm going to start by plotting the points that I found. Let's see, we had a y-intercept at 80. We had x-intercepts at 2 and negative 2. And then also at plus or minus root 20, which is the same thing as about plus or minus maybe 4.5. So those are all the intercepts we found in part B. In part C, we found out that this function has a local min and local max. The local max was at this point 0, 80, and our mins were at 3.5, negative 64, and negative 3.5, negative 64. Our inflection points were at x equal 2, y equals 0, and x equal negative 2, y equals 0. And then finally, we are going to connect the dots using the information we got about this function increasing, decreasing, concave up, concave down. In part C, we showed that from negative infinity to negative 3.5, the function was decreasing. And then it was increasing from 3.5 to 0, decreasing from 0 to 3.5, increasing from 3.5 to infinity. The inflection points were places where it changed from concave up to concave down. It was concave up to that first inflection point. Then it was concave down. And then finally, it was concave up again. So to connect the first two dots, I've got decreasing and concave up. The second two dots, it's now increasing and concave up. At that inflection point, it shifts to concave down. And then after the max, it's decreasing and concave down. At the inflection point, it shifts and becomes concave up. And then at the min, it shifts and becomes increasing. And so in blue is my very nice sketch of this graph, including all of the important information. All right, once again, there's a lot of material in this section, so please don't hesitate to ask if you're struggling with any parts of this.